Chapter 4 today, discussing carbon and climate change. And we're going to spend some time at the beginning talking about carbon and how we can change between the quantities called moles to the quantities called mass. And then afterwards, we'll talk a little bit about the structure of carbon and other simple molecules. The reason that's important is because the three-dimensional structures is what causes some of these molecules to behave the way they do. And in particular, we're going to spend time talking about carbon dioxide and how its three-dimensional structure is responsible for its ability to trap heat and therefore act as one of the greenhouse gases that causes global warming. One of the reasons that carbon is important is because carbon dioxide contains carbon, and carbon dioxide plays an important role in keeping heat on Earth, thereby raising the temperature of Earth on average, which is what we call global warming. Now, carbon itself is an element that you see in a lot of different compounds. They're all covalent compounds, generally speaking, because carbon is in the non-metal part of the periodic table. We actually have a branch of chemistry that studies just carbon-containing compounds because of how many of these compounds exist. And that branch is called organic chemistry. There's a lot of different organic compounds that we use every day. These are just some of the examples that you might have come in contact with. More importantly, all of the biomolecules that we have in our bodies are all carbon-containing compounds. So the carbohydrates, lipids, proteins, and nucleic acids, the carbon that we have around us are always recycled. So this is done through what we call the carbon cycle, where we take in carbon in the form of sugar and we break it down, and then in the end we exhale carbon dioxide into the atmosphere. Sunlight and carbon dioxide is then combined in plants through the process of photosynthesis to generate sugars, and then that cycle starts again. In recent years, the quantity of CO2 has gone up beyond just this natural process of the carbon cycle. And so because CO2, as you'll see later, can trap heat, this results in the gradual warming of the planet, and we start seeing unwanted consequences as a result of that. For us to be able to determine how much carbon exists on Earth and to determine the effect of that quantity on global warming, we have to learn how to convert between mass of carbon to something we call the moles of carbon, or the number of atoms or molecules of the carbon-containing compound. So to do that, we need to get into a little chemistry. So we're going to look at two quantities here. One is called mass and the other one is called moles. So mass of an atom comes from the three subatomic particles, protons, neutrons, and electrons, that it contains. Because the mass of these subatomic particles are so small, a lot of times it doesn't make sense to use units like grams or kilograms to express these masses. The way we simplify the representation of the mass of atoms is just to express it in something called the atomic mass unit. One atomic mass unit is just equal to the mass of one proton. So if somebody tells you that the mass of an atom is 12 atomic mass unit, that means that it contains the equivalent of 12 protons in it. Now, it could be 12 protons, it could be 6 protons, 6 neutrons. So it could be some combination of those things. The other thing that we do not count, just to make life easier, is the mass of the electron. And the reason is because the electron is way lighter compared to the other two subatomic particles. Adding them into the mass calculation doesn't really change the number. This illustration just shows you how the masses of the subatomic particles compare to each other. Neutron is about equal to proton, whereas electrons is really, really light, so light that in fact you need 1,830 electrons in order to equal the mass of one proton. So that's why we don't really include mass of electrons in totaling up the mass of an atom. Another thing that complicates the situation in understanding the mass of an atom is that an element may have different isotopes. So isotopes are just atoms that have the same number of protons but different number of neutrons. The reason I'm showing you this is because carbon has different isotopes. All carbon isotopes have 6 protons, as you can see here on the top, but different number of neutrons. So this isotope of carbon, which we call carbon-12, has 6 protons and 6 neutrons. Those of you who are mathematically inclined might be able to see quickly that the reason it's 12 is because it's 6 plus 6. On the other hand, we have a carbon-13 isotope where there's 6 protons and 7 neutrons. And then we have a carbon-14 isotope, which is really rare, and that has 6 protons and 8 neutrons. The carbon-12 is the most abundant. Almost 99% of all the carbons that we find on Earth is in the form of carbon-12. About 1% is carbon-13, and very, very little is in the form of carbon-14. Because there's different isotopes of carbon and other elements, we can't really find one specific mass to represent the mass of carbon, because if we say the mass of carbon is 12, it's not quite right, since there is 12, but of course that's not all of the carbons that we have. There's also some 13 and some 14. So what we do in order to express the mass of an atom of carbon is to average out all the masses of the 3 isotopes based on their abundance. That number is what you see in the periodic table. When you look up the periodic table, you have the symbol of the element, you have the atomic number here on the top, which is just a whole number that represents the number of protons. You learned that before. And then there's another number written at the bottom, which is usually some kind of a decimal number. And that number is the average atomic mass, which is taken into account from all the isotopes that exist for that element. We can take a look at some example here. If you want to find the average mass of a chlorine atom, all you need to do is go to the periodic table. You can see here that it says 35.45. So that would be the average atomic mass of a chlorine atom. Now the unit there is going to be that atomic mass unit that I described earlier, or AMU. The second question here says, what about the mass of an atom of a chlorine-35 isotope? In this case, that mass is going to be exactly 35 AMU. So when they tell you it's a specific isotope, then the mass is just whatever number that's listed there. The AMU unit that we just discussed is not really useful in practical mass measurement, because we don't really have a scale that measures in units of AMU. The scales that we have measures in units of grams or other units like pounds, kilograms, but nothing that has the unit AMU. To make the mass unit AMU useful for us, we have to relate it to these other units that we actually use. And in chemistry, we use this conversion factor that is called a mole, and a mole is just the same as 6.02 times 10 to the 23rd of that item. So if we're talking about a mole of an element, that means that there's 6.02 times 10 to the 23rd atoms of that element. It could be any other particle. Why did we use this number? It seems kind of an odd number to just pull out of thin air. Well, the reason is because if you use this particular conversion factor, it actually allows us to use that same exact number in the periodic table that we just used earlier to find the average mass. That specific number would then be also equal to the mass in grams of a mole of that same element. Okay, so let me make it clear by giving you an example. Here's the periodic table symbol of carbon. If we have an atom of carbon, the average atomic mass of that atom is 12.01 atomic mass unit. Now, if we have 1 mole of that carbon, we're going to have 6.02 times 10 to the 23rd carbon atoms. Okay, that's obviously a lot of carbon atoms, right? The question then becomes, what is the mass of that huge number of carbon atoms? Well, it's going to be the same exact number, but in unit of grams. Okay, so you would say that the mass of 1 mole of carbon atoms is 12.01 grams. Okay, so you see how you use the same exact numbers in the periodic table, but different units. And it's for different quantities of carbon atoms. So the AMU unit is for 1 atom. The grams unit is for 1 mole of atoms. So let me explain a little bit this idea of a mole, because a lot of times students have difficulty understanding it. A mole is like a group unit. It's very similar to a dozen. When we say a dozen of something, we always mean 12, right? Most typically we apply this to eggs, but it could be a dozen of anything. So when I say I want a dozen packs of boxes, that means I want 12 packs of boxes. If I say I want a dozen pieces of metal, I mean I want 12. So when I say I want a mole of something, that means I want 6.02 times 10 to the 23rd of that thing. So that's literally what mole means. Okay, this is such a special number that we call it Avogadro's number. That's the name of the scientist who discovered this relationship between particles and moles. Okay, once you understand this concept of a mole, we can define a quantity called the molar mass. And that's just that number that we just figured out earlier for a mole of something. So for example, for carbon, its molar mass, which is the mass of 1 mole of carbon, is 12.01 grams. So we would say 12.01 grams per mole is the molar mass of carbon. Okay, so it's 12.01 grams for each mole of carbon. If you want to calculate the molar mass of a compound instead of just an element, you just need to add the molar mass of all the elements in the compound. So here's a quick example. What is the molar mass of carbon dioxide? In carbon dioxide, we have 1 carbon and 2 oxygens. So we're going to take a look at in the periodic table for the molar mass of carbon and oxygen. You find carbon, of course, we already said it many times, is 12.01. Oxygen is 16 here. What I'm going to do here is I'm going to take the molar mass of carbon, which is 12.01 grams per mole, multiply by 1. Really what we're referring to here is that there's 1 mole of carbon in carbon dioxide. And then 16 for each one of the oxygens, and then multiply by 2 since there's 2 oxygens. After the multiplication, we add up all the numbers, we get 44 grams per mole. So that would be the molar mass of carbon dioxide. Let's work on the problems of calculating molar mass that we just saw in the example. So I'm gonna show you where that problem is in the notes. It says, what is the molar mass of CH4, which you remember is methane, and NH3, which is ammonia. The only thing you need to do here is to use the periodic table to help you calculate this. So CH4, if you want to calculate that, you're gonna need to find the molar mass of carbon. I'm showing you on the left there, it's 12.01. We only have 1 carbon, so it's gonna be multiplied by 1. And then for hydrogen, we have 4 of them. We're going to need to find the molar mass of hydrogen. It's 1.008. You multiply by 4. And then you just add all those numbers together. You get 16.04 grams per mole, as shown right here. Ammonia, NH3, you can follow the same steps. You should check for yourself that the answer is 17.03 grams per mole.